So yes, I'm going to talk about PGAS languages. I'll actually spend most of the time, just to be concrete, on UPC. Brad's going to talk a little bit right after me, I guess, on another language in this class, but it's fairly different, called Chapel. So I'll let him really cover some of that, the rest of that space. But I'm going to give you an idea of what these PGAS languages, Partitioned Global Address-Based Languages, are about, and specifically then how you might program in UPC. I'm actually not the NERSC director anymore. Sudeep Dosanjh took over as NERSC director. NERSC is one of the things that's in the Computing Sciences program at Berkeley Lab, so I think you're most familiar with the Argonne Leadership Computing Facility probably from the previous discussions, but just to give you a little bit of an idea of what NERSC is like, it's another computing center similar to the ALCF, but has a somewhat different scope and different numbers of users. So we've got about 4,500 users that come from all over the US, actually around the world, and 600 different projects, which means that each of those projects has an allocation of time that it charges against. A lot of students from universities and postdocs and so on, and a lot of papers get written by it from the computing. There's a picture down at the bottom of our fastest machine right now, which is Hopper. It's a Cray XE6 system. We're actually in the middle of installing another system that'll be called Edison. We had a little baby version of Edison that was up and running and very popular with the users, but the full system is coming in actually as we speak. It's being, I think all of the cabinets are on the floor and it's being hooked up and so on. Now we run a very diverse workload of applications, and I wanted to say a little bit about this because it kind of speaks to the topic of this lecture, which is why would you be interested in anything other than MPI or maybe MPI plus OpenMP? Just to give you an idea, there are applications that are running in production at NERSC that are written with other things other than MPI. That you can see the breakdown there. About 75% of the codes are Fortran codes. 45% use some C or C++. Often, as you can tell by adding those two percentages together, they're mixed. Those languages are mixed together. Python is an interesting story. It's a small but growing part of our workload. Now, not that they're writing full applications in Python, but there's a lot of Python that's being used to glue together much more complicated applications from components to build workflows and things like that. So I'll say a little bit more about that later. About 85% MPI applications, 25% they say have OpenMP. That number is also growing substantially because of the large number of cores we're seeing per chip. And so it really doesn't make sense to run just a flat MPI application, at least in the performance that we've been looking at so far on the memory footprint. So 10% are PGAS or some kind of a global object library. Not all languages, so some of these are libraries. There's a library called Global Arrays that is used within an application called NWChem that's very popular, and these are all of the kind of communication layers that are things other than MPI, and that's about 10% of the applications. However, these numbers are reported by the principal investigators of the NERSC allocations, so these would be like your faculty advisors who may or may not know actually what you're writing in your code. So take these numbers with a big grain of salt, but anyway, it gives you some sense of the kind of diversity that we see on the systems. Now, you've heard about OpenMP, you've heard about MPI, and I'm trying to just sort of summarize what I see as the advantages and disadvantages of those two programming models. The shared memory programming model in something like OpenMP or pthreads or one of those other kinds of shared memory domains has the advantage that it's very convenient. It's easy to share data structures. You can create shared data structures and then can often parallelize some programs just by annotating the loops. So it makes it much easier to program, and even if you have to change your program a little bit, it's often very close to what the serial program looked like. The disadvantages is you don't really have locality control. You can't say where the data is supposed to live in the address space. And for that reason, you don't write an OpenMP application, for example, that runs on 100,000 or 1 million cores spread out over a network, an interconnect network on a supercomputer. So that's what I mean by not scaling kind of beyond the node level. And you have race conditions that come up because you've got these shared data structures that you're reading and writing to simultaneously. So message passing, well, you've got the locality control you're missing from shared memory. The communication is all explicit in the code, so that it's very transparent to the programmer when they're doing something expensive. Communication is much more expensive than computation. That's an advantage in my mind, that you really have a good performance model of the system in it. The disadvantage is you typically need to seriously rethink your application, and in particular the data structures. You need to think, if you've got a big graph, a mesh, for example, that you're simulating a some kind of a structure that airflow is going over. You have to really think about how are you going to take that data structure, chop it into pieces, what is each processor going to own, how are you going to keep the pieces kind of connected together, where are you going to put them, are you going to try to put them nearby each other on the machine? So it just requires a lot more work. The other thing which is not nearly as interesting is you write a lot of pack and unpack code in MPI. And this was something I realized is sort of different than the hard problem of thinking about how am I going to partition my graph, what kind of an algorithm will I use for that. And it was a graduate student of mine many years ago who had been doing parallel computing for a long time. And he said to me, I hope I never have to write another pack and unpack routine. And in fact, he's actually working in databases now where he may still be doing packing and unpacking, but he's not doing HPC. So it was just, it was a very smart graduate student, but felt like maybe he'd written his last pack routine. And then the last one, which will really come up kind of in this PGAS model, is not knowing when to say receive, that you have to figure out where to put the receives. And in some applications, that's completely obvious because you go into a communication phase and you have one processor sending, another processor receiving. Maybe all processors are sending and all processors are going to receive afterwards. So it's very easy to figure that out, but in other cases, it's going to be very hard, and I'll talk about that. Now here's a little experience from running MPI on a system with, in this case, it was actually the Jaguar system with 12 cores per node. And so this is a shared memory node, and the two different graphs that are superimposed there, one of them is running time, so down is good on the red bars, and the other one is memory per node that's being used, and so down is also good on that one. So you're trying to get the minimum of both of those two things, and what you see is that they're not at the same place. So each one of those bars represents exactly the same amount of hardware as every one of the other bars. So the only difference in running time is coming from the difference in cost in communicating and the way that they're communicating. So there's no different, and perhaps the memory system effects from the way things are laid out in the two implementations. On the far left, you have an MPI process per core. So number of OpenMP threads is per MPI task is just one. There's no OpenMP being used on the left-hand side. So in that case, you have a big memory footprint because MPI has itself copies of things that are needed inside the implementations. And of course, the MPI people who are doing the implementations are working on reducing that footprint. But you as an application programmer also need to replicate some of your data structures in order to make the MPI data structures kind of all hang together. So you've got a bigger memory footprint on the left, and but now it's also a little bit slower because there's more overhead for sending messages in between the cores that are in the same chip. As you add more OpenMP threads, you get better performance, you get a better memory footprint. At some point, though, the performance turns around. And so what we see across different applications, I believe it was a material science computation that has a 3D FFT in the middle of it, so it is fairly communication intensive. So the effects may be somewhat smaller on other kind of applications, but we see graphs that look very similar to this on other applications. And what's consistent across those graphs is the memory line. Now, the memory line always drops as you add more OpenMP parallelism. Exactly where the optimal point is in terms of performance depends on the machine architecture and depends on the application. And so that can vary a little bit. But the point is, when you mix OpenMP and MPI together, you also have to make this decision about kind of how much parallelism to use. You can, as I said before, if you tried to run a pure OpenMP model, you really wouldn't have enough control over locality to be able to expand it to the entire machine. And the last point here, which is really what I was talking about, is that the tuning is not obvious exactly how you want to make this point. So it's not, I'm not saying that you shouldn't program in this model. In fact, it is what we recommend at NERSC, for the most part, is people that are programming that use MPI and add OpenMP to it in order to take advantage of the shared memory that's on the node. But what about this idea of never having to say receive, and where does that come up, and what are these partition global address space models about? I put this slide together at a very high level, and I can see the graph isn't showing up so well on the right, but roughly speaking, if you think about most of the message passing programs that are written within the DOE labs, even written within the NSF centers, they're physical modeling and simulation programs. Physical models have a lot of locality in the world in them because the world tends to be a fairly localized place. Now, that doesn't mean that you don't have Poisson effects and things that have long-range effects that you have to implement in your applications, but it is fairly easy to take the globe and to chop it up into pieces and hand each piece to one of the processors and then figure out how to do the communication in between them. So message passing works very well in problems that can be domain decomposed pretty easily. And there's kind of a sketch of what an MPI program looks like, and maybe you've probably already written something that looks like that. And in a global address space program, you may also have something that looks kind of like a graph, but rather than having a physical structure to it, one of those is the web connectivity graph, and the other one is some other kind of Twitter traffic or something like that. So these are graphs that are very unstructured. And you could say, well, we could partition those graphs, and once we partitioned those graphs, once we figured out kind of what was nearby what in those graphs, then we could come up with a good model that would work within message passing. But the problem is that partitioning those graphs is typically exactly what you want to do. That is the problem. The problem is trying to figure out what's related to what in those graphs, and whether this is coming from genomics, a computational biology problem, or it's coming from one of these kind of commercial applications, or is coming from trying to put all kinds of heterogeneous data sets together from different science simulations and experiments. Basically, the question is, what is the relationship between things? So you don't know when one processor tries to send a message to another one, the other processor doesn't know, so to speak, when to say receive. We can kind of look at the spectrum of kind of irregularity in applications, and this is a loose kind of notion, but we can think about the types of applications that we run at NERSC, that we run at ALCF and others. The first kind of parallelism you have on the far left is massive independent jobs. They really are separate jobs. We sometimes actually pack those into a particular MPI program in order to make the job run more easily on these systems that are designed to run large jobs, but they don't really depend on the network very heavily. Things that are nearest neighbor simulations have a little bit more, they have more communication in them, but all-to-all kind of computations that come up with something like a 3D FFT, much more communication intensive. And then the last on the right-hand side are these random access sorts of problems. So PGAS languages originally were designed for this right-hand column, that is, things that really have random access in them, where you can't a priori say, what is the structure, and therefore when am I going to do my communication, because you don't know what the structure of the problem is. It turns out that we discovered over the last decade or so of working on these PGAS languages that they're also very useful in doing all-to-all kinds of computation, and that's because the communication mechanism used in the PGAS languages is called one-sided communication, and I'll say more about that later, but it means that you can send lots of messages into the network and send them more efficiently than you can in a two-sided model, which ties up synchronization into the process. MPI has a one-sided spec to it, so I don't mean to say anything about whether or not MPI one-sided. I think it probably will be able to get all of the benefits that you get in that kind of an all-to-all case, and maybe even the random access case, but that part of the spec has typically not been as well implemented, so when we've tried to use it for experiments, we've found that it hasn't performed as well. I think that is changing, largely due to some of the work here at Argonne and making the one-sided stuff go faster. But I'll just talk about PGAS as a one-sided model, and you can try to translate that into one-sided MPI if you want to think about that as well. So what does a PGAS language look like? I've talked in abstract terms so far. What the word partitioned global address space language refers to, or partitioned global address space even for a library, is it's got a global address space. So that means that a thread can directly read or write data that's remote in the system. It doesn't necessarily mean that it can read or write any data in the system, but it has the ability to read or write data in the system. There's going to be some data that sits in the shared address space or the global address space, and that data can be written. So you don't have to own the data in order to write it, and it's fairly different than a message passing model where you have to get the processor on the other side to read or write the data for you. It is partitioned because we have the ability to say what's local and what's global. That is, we're going to take data structures as an MPI, and we are going to spread them out. So some of that complexity that you got in MPI will also come up in a PGAS language because you have to control your locality. And I think that's necessary for scalability, so it's not something that I consider really a disadvantage, although it does mean that there's more work in writing the program. Here's our standard cartoon of what a global address space looks like. It's got some processors or threads. I use the two terms processor and thread, or process and thread, somewhat interchangeably because some of the languages actually use the word thread and some of them use the word process. And the reason is because if you go back to kind of the Unix notions of process and thread, a process is something that has a separate address space. A thread is something that has a shared address space. We're somewhere in between the two, so different languages made different decisions about which terminology to use. They do not have to be tied to physical processes. They can be tied to a node, and you can have some other kind of multi-threading underneath that if you want to. But just for kind of convenience of thinking about it, think about a processor associated with each one of these processes. And it has a little bit of data that's private to it, so think of that as the program stack. That is all the variables that you declare within your functions go into the private part. Other processors can't see into those. But then when you allocate things like large shared arrays or other linked data structures, there's kind of a linked list that's shown here. Those they can go into the shared space, and then other processors can walk around in that linked list if they want to without asking the program on the other processors to help them. So I'm going to talk now more specifically and more concretely about UPC. I'll say a little bit about the background, and then I'll really tell you about the language. The initial language design was done in 1996. When it actually started, it took a little while to get that tech report out. So the tech report actually came out in 1999 and was led by Bill Carlson and others at another government lab, IDA. And it was based on putting together 3 languages that had already been fairly popular, at least in the research community. One of them was Split C from Berkeley. Another one was PCP, language with probably the worst possible name from Livermore, and AC, language from IDA. So those languages it was an effort to kind of merge those because we had some experience with them. Then there developed a fairly large consortium of companies and other universities, and so it's a project that goes well beyond Berkeley at this point. And if you're interested in being involved in the language spec, it's a fairly open process, and you can get involved. We have phone calls with some regularity, and actually we have people at Berkeley and people at Intrepid, which is a small startup company that has a GCC-based implementation of UPC, are really kind of pushing that spec process at this point. There are multiple compilers. There are compilers in the Cray system. There actually is an IBM compiler, although as far as I know, it's not a product that is running on the Blue Gene system, so on Mira, but you can use the Berkeley compiler, which is a source-to-source translator. So we have our own compiler that we release, and that's what we use when we run the Blue Gene systems, and you'll see some data from that later. So let's see, in terms of what UPC actually looks like, well, like MPI, you have a notion of how many threads there are in the world, and a notion of which one is the ID of the thread that's executing a particular program. It's a single program, multiple data model. So there's a fixed number of threads. They start at the beginning of the program. They run to the end of the program. You don't dynamically create and destroy threads. And then there's a UPC barrier, which is a global synchronization that works just as it does in MPI. There's actually some variations on that. There's a thing called a split phase barrier. One of the philosophies behind UPC is to try to minimize the overhead of every operation that you're doing and try to let the programmer get the most performance out of the machine that's possible. So barrier can be very expensive on a large machine. One of the ideas is that you can initiate the barrier saying, this thread is ready to go into the barrier. I'll keep doing some other work that's unrelated to what the synchronization is about and wait for all of the other processors to reach the other end of the barrier. Let's talk about another kind of a loop later. And there's a couple of different compilation modes, and this just is something that I won't talk a lot about it right now, but it's important to understand when you write programs, because if you start using the threads variable in the wrong place in, for example, declaring array, it is not necessarily a compile time constant unless you compile it in a way that makes it a compile time constant. C doesn't let you put them in lower dimensions of arrays. So let's see, here's just your Hello World program in UPC. It is, first thing to know is any C program is a legal UPC program. It is a strict superset of C, and that is of the ISO C. And it's, if you compile and run a C program as a UPC program with P threads on it, you're going to just get P copies of that program running, so they'll all be doing the same thing, but not very interesting because they'll just redundantly compute the same answer. We can therefore write this very simple UPC program that is just doing hello world. Using the my threads and threads variable, so it hopefully is fairly obvious. Exactly what happens in terms of the order of the print statements there is not well defined. There's no synchronization saying thread 0 gets printed before the others. Whether or not the text actually gets kind of mangled up on the screen also depends a little bit on the thread safety of the printf library that you're using. But for most implementations, this program will behave in some reasonable way. So a little bit more interesting example is we're going to do a Monte Carlo pi calculation that is just throw random darts at a little unit square, and then we're going to just calculate whether or not, when we get an x and a y value, whether or not that x and y value indicate that that point is below in the red part, inside the circle or outside the circle. Use that to calculate 1/4 of the area of a circle, multiply by 4, and get pi from that. Here's what the code looks like in UPC. And this is now actually the kind of C version of it, so it's just computing pi, so independently on each one of the processors. So you can do all of the things you can do in C. So how many of you are C programmers, kind of familiar with? Oh, great. Okay. Sometimes I talk to a whole room full of Fortran programmers, and they look at this like, what is all this nonsense? But so some of you I noticed did not raise your hand, but I'll try to give you a pretty good idea. Hopefully, it's mostly obvious. The argument passing for inputs is a little bit arcane in C, and UPC inherits that. So you ask how many arguments you're passing in, that's argc, and then the chunk of arguments is passed in as array, which has that weird looking syntax there. There's a little bit of text to convert those into integers and so on. And then we're calling a random number generator there in order to, and we're initializing a random number generator there, srand. We have to be, by the way, a little tricky about random number generators in parallel code, but let's just not worry about that particular problem for right now. So what happens in the parallel implementation is each thread gets its own copy of these variables that you've declared, because they're just regular old C variables, and that's the default of what happens. Each thread can use all the input arguments, so that's kind of nice. They all get a copy of the input arguments, and they're going to initialize this library, as I said. Here's where the actually interesting part of the computation happens. There's where you're calling the random number generator. It's actually happening inside the hit function, but it's just a little bit of C code that calculates a random x and a random y, and then figures out whether or not it's a hit inside the unit circle or not, and it returns either 0 or 1 depending whether it's inside or outside. And then you're just accumulating those things together, and you compute pi. Now that program works. There's both a little bit of the .h stuff, the header stuff that I couldn't fit on the previous slide, and there's the hit function. Just regular old serial C code, as I said. So it's not a very interesting program at this point, because you're using your processors to all do the same thing, and they're not helping each other out. In order to make something more interesting in UPC, we need to understand how to use shared variables. So normal C variables are just allocated in the private, that is the white part of the address space, where other processors cannot see them. And what we want is something that's shared so that they can share some work. The simplest way to declare something, and I'll just say right away, this is rarely what you want to do in a real high-performance UPC application, but is a good way to sort of understand the sharing semantics, is you just declare another int, which is called ours, and it's shared. It goes on thread 0, so it has affinity to thread 0. It lives in that part of the address space over there, but it is visible to all of the other threads. These shared variables cannot have a dynamic lifetime. That is, they can't be declared inside of a function. Anybody want to tell me why? So the answer is that if they're inside of a function, some threads can be in that function, other threads are not in that function, because there's nothing that says all the UPC threads have to be doing the same thing at the same time. And so if you declare something inside of one of those functions, then and that variable, maybe thread 0 is still has exited the function, and so the ours variable is gone, but some other threads are still sitting there, think that a variable exists and are trying to access it, so they're going to be accessing some garbage. So for that reason, you have to put them in a place where they're going to be always available, have a lifetime that extends past functions, or a static lifetime, or something that can be dynamically allocated but is under your control, such as using a malloc. Okay, so here's a little version, though, that uses such a variable. We put the shared variable up there outside of the main function, and it is going to record all of the hits across all of the different threads. We're going to actually divide up the work evenly across the different threads. Whoops. So we're just dividing by the number of threads with a little rounding it there done to try to make sure we get the right number of trials. And then we just call the hits function inside of a loop. And that's being accumulated now in this shared variable. So every time you get a 1 back, or for a 0 for that matter, you're adding either a 0 or 1 into the hits variable. And then then one of the processors prints out the answer at the end. Problem with this program, when you're accumulating into the hits variable, it's not necessarily atomic. So there's a race condition in this program. You have a variable hits that's being read and written simultaneously by the different threads. What's kind of, to think about these race conditions, what happens in kind of the hardware level is you think about it, you go and read the old value of hits, you add 1 to it in a register, and then you put it back. If 2 threads are doing that at the same time, they both read the same value, they both increment it, and they both write the same value back, and so you lose one of the increment operations. So this program doesn't actually work correctly. It also has another problem, which is performance. So it gets the wrong answer and performs very poorly. Other than that, it's a great program because we've got this one variable sitting on thread 0. So you've got 1,000 processors, and they're all bashing on thread 0's network interface in order to get into the memory that's sitting on that thread. So not a good way to write the program, but it does actually work. And if it's a small shared memory machine, we could fix this by putting locks around it, and it would work just fine. Because we want to write things that are scalable, let's talk about a way of fixing the program that would actually make it more scalable. In order to do that, we'll make a shared array rather than a shared, just a shared scalar variable. So here's how we declare a shared array. We just put it before an array declaration. There again, for those of you who are not used to writing C programs, the easiest way to read these declarations is from right to left. Not left to right, but right to left. So X is an shared array of ints. I guess not entirely in this case, but when we do pointers, we'll read them that way. So the first one is one element per thread. The default layout is what's called a cyclic layout. So that means that each thread will get one element of the array, and they'll just get wrapped around. And so the first declaration of X there, it has threads elements. So if you declare that and you run the program with 4 threads, then you're going to have each thread having one of those elements. And so what's highlighted there is the element that thread 0 has affinity to, kind of owns, if you will, in the sense it's nearby. And so it's the 0th element of X and Y and Z, and then Y and Z are bigger, so they get wrapped around a little bit. Z is a multi-dimensional array. It's a 3x3 array, but unfortunately C has pretty weak multi-dimensional arrays, and usually if you're going to do anything very complicated with them, you need to think about the fact that they're really just laid out as a linear chunk of memory. So for better or worse, C exposes to you the idea that a 3x3 array is just a big flat chunk of 9 elements of memory. And so that's how it gets laid out in UPC, is cyclically based on the idea that it's just a 9-element array. We can think of these things, I guess, a Y was also a 2-element array, and we can sort of think of that as being logically blocked by columns because thread 0 owns each one of the elements in the first column of that 2-dimensional array. These are tricks that I tend to not try to use too much in UPC, but it is good to understand what the memory layout looks like. Okay, so here's a shared array version. Rather than declaring our hits, we'll declare all hits, which is going to accumulate all of the hits, but it's going to be an array. And it's going to be an array of threads. It does have to be compiled in static mode because this is the case I talked about where C will tell you if you're going to declare an array of that size, I have to know at compile time what that value is. Now when the initialization code and so on is the same as before. So now what I'm doing is when I'm accumulating the hits, I'm writing into my element, the element that I have affinity to. So that's two advantages. One is I've eliminated the race condition because each thread is now writing a different element of the array as it's doing the accumulations. And the second advantage is that it should perform pretty well because those local accesses are just going into the memory that's on your node. There's no network traffic, no communication involved. And then once you've done all those accumulations, thread 0 is going to go through and just add up all of the results. So it can read all of those things. So that's a fairly slow loop there at the end. But the assumption is that most of your computing is done up there earlier when you're doing the computation. At the end, there's a little bit of serial work done just to add things together. We can fix this program, as I said, other ways. We can make that accumulate loop much more efficient by using reduction operation, which is supported in UPC, but this program will work if most of the work is up there in that hits function. Unfortunately, the hit function actually doesn't have much work in it, so you need to throw a lot of darts before this starts to scale very well. The shared variable has is in the yellow part of the address space, so it's shared, so every thread can access it, and element 0 of all hits is sitting there where ours is. Element 1 of all hits is sitting in the same place but under thread 1 and so on. So that array is physically laid out on each one of the threads. The easiest way to think about this right now is assume that you have a distributed memory machine. Don't think about shared memory machines because it actually is more complicated to implement and more complicated to think about. Just think about the idea that each processor has a piece of the shared space that it has affinity to that's nearby. So think of it as a processor and its memory. It's going to assign a little bit of the memory is going to be private memory that nobody else can see, and then the rest of it will be shared memory that the other processors can see. So all hits has one element in that shared spot for each one of the elements, so it's really distributed across them. if we wanted to write this in a style that uses synchronization, just to point out that we can actually do this, UPC has the regular barrier that you've seen in the examples so far. This is the way you write the split phase variable barriers that I mentioned earlier. You say UPC notify and UPC wait. So where is this useful? This would be useful if, for example, you have a problem in which you've chopped up a big array and you need to compute the exterior, the ghost regions, if you will, of your local array, and then everybody else needs to read them. And after you compute those exterior regions, you can compute the interior regions, and no other thread cares about the interior. So what you would do is compute the exterior first, then say UPC notify that says anybody else, I'm ready to do this barrier, and after the barrier everybody can read my data that I've written, but in the meantime I'll go and compute some other stuff and then do UPC wait when I really need to get the data that other processors have. And so in this way you can speed up some applications by separating, if there's a little bit of load imbalance in the system and not all of them are ready, you can keep the processors busy a little bit longer by using this kind of a split phase barrier. There's also labels in UPC. This was put into UPC to make programs easier to read. So you just define, they're actually just integers that are the labels, but you can give them names in C. So this just defines a constant name merge barrier. And so you write these kind of programs that have a barrier that occurs in two different places in a conditional, but they will actually line up at runtime. And so here the even processors are going through the if branch, the then branch, and the odd processors are going through the else branch, and they're both going to hit the barrier. So the program will eventually have it should work correctly because all the threads will eventually hit that barrier. But just to make it easier to read that code, you can give those a label. Well, locks are a new type in C. We call it an opaque type, meaning that a different implementation of UPC can use their own representation of locks, and the user doesn't get to see what's inside of those, so that makes your code more portable across implementations. The locks have to be allocated before you use them, so there's an alloc statement. There's a way of doing it globally. The first one is allocating a pointer to the same pointer goes out to all the threads. The second one is, so that's these all underscore functions in UPC. The convention is those are collective operations, so it's typically the case that if you have a lock, you want more than one thread to know about that lock, otherwise it's not a very useful lock. So in the example of the Monte Carlo pi calculation that we had before, in the version where we were all going to bash on the our hits variable, what you would do is you would all allocate a lock together. That lock is going to, by the way, live on thread 0 also, where the variable lives. And then whenever you, and so you'd use the all lock to do that, so you'd all get a pointer to that lock back that you could use to ensure that the code is protected, the variable is protected. Typically, though, you may also want, you may just want a few threads to have access to a lock, so then you would do it with a global alloc, and you somehow have to communicate that lock to the other threads that need the lock. You could do that by writing it into a data structure. You can do it by broadcasting it or other things like that. So then when you use a lock, you just say lock and unlock, and you should free them in proper UPC programming style when you're done. Otherwise, you might run out of space later. But that's just the special way of freeing them up. So here's the version of the program that had the hits variable. Sorry, it wasn't called R hits. It was just called hits. That had the one shared hits variable. Remember, declared at the top there. You allocate the locks up here in the code, and then you have your, first of all, so that you're not bashing on the lock all the time. You could put the lock around this statement right here, but instead what you do is you lock when that thread is done computing its local copy of locks. You do a lock on the shared hits variable, and then you increment it. So this is serialized like the previous version that I showed with the array, but it's done a little bit differently in that different threads are going to do the updates on that shared variable, but they're going to do it by locking and unlocking the variable. So this program also works. It's reasonably scalable until you get to that last piece of the code. Okay, so what have we seen? We saw private variables. We saw shared scalar variables. So private variable, private scalar variable, so scalar just means not an array, and we've got scalars like my hits and hits is the shared version of that. Then we had shared arrays like all hits. We can also have non-shared. We can have private arrays if we want to. We can still allocate things down in the private space. And then we had shared locks, and those were kind of the different kinds of variables that we used in this example. Now, to get something that's more scalable for that update operation, you want to do some kind of a collective. What does collective mean? You've heard about these in MPI, but it really means you want to get the threads together to do something. And I think collective really, it goes along with the idea of the single program multiple data model, that you have all these threads that are running from the beginning of the program to the end, and you want to gather them together to do something in common. So you'll collect the threads together to do something like compute the sum of a bunch of integers. There are a bunch of collectives. Here's an example, first of all, of using a collective. It's the reduced collective. It's called the values collective. So it's called all V because underscore all, as I said before, means all the threads are going to do it together. V means it's a value-based collective. We're not adding up an array. We're adding up a bunch of individual scalar values, one per thread. It's a library that came from the Berkeley group, so it's got the label BUPC on it, but it is a library that should work with other compilers. It's written in UPC, so it's not really specific to the Berkeley implementation. So this is the same code that we had before. There's the include file to get the definition of the collective, and you can download it, by the way, off the web if you want that .h file to use with some other compiler. And that's the way the reduction looks. It says I want to reduce an integer, a set of integers. The integer that each thread is putting into it is the my hits integer, and thread 0 is the one that's going to get the answer at the end, and we're going to do an add operation to combine the results together. So that's how you have the type, the input, the thread, and the operation that you're performing, and the result that comes out of reduce is returned by it. It's a little hard to see maybe because of the line wrapping there, but my hits on thread 0 is actually going to get the answer, so you can print out my hits at the end. You don't need the barrier anymore in the program because it's implied by that collective operation, and you no longer need the shared hits variable. So this is much more scalable code than either of the other ones that we talked about that worked, because you are hopefully doing the reduction in some kind of a binary tree or binomial tree or whatever, some kind of a scalable logarithmic data structure. A little bit more about these value-based collectives, which are the ones I recommend that you use. There's that all reduce statement, all V reduce statement that you saw before, and there's what the formal signature of it looks like. It's got a type, a value, the thread ID of the thread that's going to get the answer at the end, that's called the root of the collective, and whatever operation you're performing. So this is a description of what each of those things are. But there are also things like scans. Those are parallel prefix type operations. If you want to get different values put into different, the partial sums, for example, put on each thread. There's also things to broadcast. The root means the same thing except it's a source rather than a sink of the results, and there's scatter and gather. So you've got a bunch of different ways that you can move things around in the system. Now UPC and the language spec actually has a more complete version of the collectives that allow you to collect over arrays, and so that you can take a 1,000 element array on each processor and say add all those arrays together, so you get 1,000. You can get 1,000 elements out, or you can get one value out. But it's a little bit more natural to program it that way because you can just point to a big shared array and say add up all the elements of this array. It causes some complexity in the semantics because threads can be writing to that array at the same point that other threads are involved in a collective on it. And whether or not that happens depends on how the collectives get synchronized. You might want to look at UPC as kind of a data parallel language. That is, I want to take a loop that is going from 1 to n, where n is not necessarily the number of threads, and I want to give each one of those threads a bit of the work of those n elements to do. And there's a convenient way of doing that. And in order to illustrate that, I'll just use a really simple example of vector addition. As I've said before, when we have a shared array, they're laid out cyclically. So we've got 3 arrays here, v1, v2, and the sum. All of them are the same size, and because they're all shared arrays, they're all going to be lined up. They're all laid out the same way. That is, element 0 lives on thread 0, element 1 lives on thread 1, and so on, and it wraps around if n is larger than the number of threads. So they'll each have 100 elements, but they'll have each 100th element in that array. So it's a cyclic layout. what we can do inside this program, and this is not using any kind of special for loop, is we can just iterate through the elements and then through the entire array, right? Go from 0 up to n minus 1, and just check to see if I own that element. And I'll say if my thread is equal to I mod the number of threads, then I own that element. Then I'll do the sum, and otherwise I'll skip that iteration of the loop. So this works correctly, but you're executing 99 iterations for every one that you're actually going to do something interesting with. That is, you're calculating, do I own this element? No, 99 times, and then on the 100th one, yes, I compute this one, so go ahead and do the addition. So it works, but it's not very fast. You're just wasting time locally. You're not doing communication or anything, but you're still wasting time. So this style comes up so frequently that we put into UPC its own looping construct for doing this, and it looks just like a C loop, except it has one extra argument in it. Now there again, those of you familiar with C, hopefully this will not look too bad. You've got an initialization part that's saying what I starts with. I is equal to 0. You've got a test that says I is less than n. And then you've got something, the loop, which says I++, for example. And then this new thing, which is affinity. And the affinity expression is going to be either an integer or a pointer. And if it's an integer, then it says if that integer mod the number of threads is equal to my thread, execute this iteration of the loop. So exactly the kind of code that we had in the previous example. And otherwise, skip this iteration of the loop. If it's a pointer, then you check to see whether the thing in the affinity expression is pointing to something that you own, that you have affinity to, and if that's my thread, and then you execute the body of the loop, otherwise you don't. So you could use something like that for running around a linked list in which all the threads start at the beginning of the linked list, and the increment operation is doing a pointer, pointer to next, so you're jumping to the next element of the linked list, and at every iteration you check to see whether that pointer points to something you own, and if you do, you're the processor, you're the thread that executes that code. So it works for pointers, it works for linked lists, it works for arrays using the affinity expression. You can actually use it because of the way C works, you can use a pointer expression also for arrays. We'll see an example of that later. So this is really just syntactic sugar for the loop that you saw before, and it's just going to do things like, what it really means is every thread executes every iteration, and the first thing it does is a check to see whether or not they own the thing that's in the affinity expression. Compilers should be able to do a little bit better than that, so rather than going through every one of the loops, it can jump by threads because it knows that it knows that the layout is by threads, or that's actually what the for loop is going to mean. So it can have rather than having them iterate n times, it should be only have to iterate n over threads times. So that's what the code it'll actually do this more efficient version of the code right here. Vector addition written with the UPC for all. It's a little bit cleaner because you don't have the test in there. It should be a little bit faster. Exactly what different compilers do with these kind of expressions does depend on both the sophistication of the compiler and also how complicated the code is. So in a simple loop like this, any of the UPC compilers should turn this into a loop that just executes the iterations that thread needs. But in something very complicated with function calls or something in your loop expression which you're allowed to do, the compiler probably won't figure it out. So far I've only talked about about cyclic arrays in UPC, but you can have more interesting blocked arrays. These are somewhat weak because UPC is based on C, and C's arrays are fairly weak. In the other language that Paul mentioned, and I'll give you at least a little bit of example of what that looks like later, which was an extension of Java. The first thing we did was to throw out Java arrays and implement our own arrays because we wanted arrays that worked well for scientific computing that tended to have a lot of multidimensional arrays. C still gets used for scientific computing code, but you really have to understand the underlying data layout issues for anything non-trivial. And you usually have to have a programming convention for how you're going to do multidimensional arrays. Here's a little program that is, I guess this is still the vector addition example, but we're going to instead do it with a block layout on the arrays. This is going to be very important if you're doing something other than vector addition, like nearest neighbor computation, like a stencil operation where you're saying average with your left and your right neighbor. That would be a really bad thing to do with a cyclic layout because there's so much communication involved. You'd be communicating with 2 threads for every iteration of the loop. Whereas if you use a block layout, you're only going to be communicating at the edge when you get to the edges. So in order to get a blocked layout, you can put a bracket with stars in it that says, give me the maximum block size that roughly evenly distributes the elements in the array. You can have more interesting things. You can have if you leave it out, you get the cyclic layout that we've seen. If you put in this star, you get a blocked layout. But you can also put in an integer, and that gives you if you have a b and some b which is an integer, it'll give you b elements, and then the next set of b elements will go on the next thread. So this is a fixed block size. Actually, one of the most common ones that we use in practice is called what we call an indefinite layout, which means that it all lives on one thread. So it's an array that is in the shared part of the space, but it all lives on one thread. So you often want to build more complicated data structures out of these things, and so you allocate a big array that's just on a single thread. So from this, you can figure out where the affinity is, and you can write your UPC for all loops. You can use an affinity expression that makes it easy for the program to work in a number of different ways. So we've seen now that we can write these kinds of programs using these affinity expressions for the UPC for all loops, but we can also use pointer expressions in here in the tradition of C. So one of the things that when we made the decision to superset C is you inherit with it the good and the bad features of C. One of the features that's some people love and some people hate is the fact that you can take any pointer in C and say plus plus on it, and it has to do something well-defined, if perhaps not sensible in the particular context of your program. And the same thing is true here. So in this example, rather than using an integer like a sub I, we can use star p1, and you can use p1 and p2 to point into the array, and then do a p1 plus plus and a p2 plus plus. And independently of whether that array is cyclic or blocked by a constant blocking factor or blocked with a fully blocked, the right thing has to happen here, and it does happen in the code. So that is that the pointer will stay on the thread for a little while and then jump if it's a blocked layout, and it implements that correctly. Okay, so we've seen this notion of this shared part of the space and these different kind of pointers. I think perhaps unfortunately one of the decisions we made early on in UPC was to use the word shared rather than the word global. And the way we tend to use it now in UPC conversations is if you're talking about pointers, you're talking about pointers to shared. And so that's an atomic phrase in UPC lingo, which is a pointer to shared, is a global pointer. That is a pointer that can point anywhere in the global address space, because it's a big fat pointer and has enough information that you can do all these operations on it, and it can point anywhere in the system. It's important to understand in any of these kinds of PGAS languages, there's the question of where the variable lives and the question of where it can point to for a pointer. So a pointer can live in the private space and point to the shared space, that would be P2. It can live in the private space and only point to the private space, that's P1. It can live out in the shared space, P4, and point to something else in the shared space, or it can actually point down to the private space. But that's kind of a weird thing to do, because now you have a pointer sitting out there in the shared space that points to something private, and nobody else can actually do anything useful with it. So we recommend that you don't write programs that way. Here's pictorially what these different things look like. So you've got things that can point up into the shared space and kind of sideways in the shared space, and unfortunately back down again, which is the thing that I would say you shouldn't do. These actually come up a lot in practice. So the regular old C pointers in star P, a declaration like that, is implemented just like a C pointer. So those pointers should run just as fast as a C pointer, because they are actually C pointers in the program. In fact, it is the case that, as I said before, any C code is a UPC code. A very common thing to do is to take a bunch of C code that's been written before and plug it in as some serial code that's going to be running on one thread. It's just the case that if some of those data structures happen to have global pointers or pointers to shared in the middle of them, that code will no longer type check, so you won't get it to compile. You'll have to go through and fix the code to be able to handle the correct pointer type. They're used a lot in real UPC application. A private pointer to shared is usually used to refer to data that is remote or potentially remote. A lot of times you'll pick a pointer like that up and check to see whether or not it's local before you do something with it. The compiler actually has to do a check for you when it uses it as well, because it has to either send a message or not send a message depending on where that thing points to. So what that means is that shared in star P, that at P2 is actually slower to use than P1, even if the data is local. So an important UPC optimization is to use the C-style pointers whenever you can. So a common thing to do is to take a shared pointer, cast it to a local pointer, and use it, or point it to shared and cast it to a local pointer. And then we, as I said, we have the last kind of point around through data structures like linked lists. What you have inside of a UPC pointer as opposed to a C pointer is the virtual address, which is the C pointer part of it. You've got a thread ID that tells you where that data lives. And you have a phase, which is maybe the non-obvious part of the implementation. That tells you where that pointer is relative to the beginning of the block because of these block layouts. So, so that when you pick that pointer up and do a ++ on it, it can figure out whether it needs to jump to the next processor or it needs to stay on the current processor. But that just gives you an idea of, you don't have to really worry about this other than if you're wondering, what are these pointers like, that's why a pointer to shared is going to be a little bit slower, take up a little bit more space, about twice as much space, and be a little bit slower to manipulate than a local pointer. UPC really is about supporting much more irregular sorts of applications, not just array-based computations. So what actually happens in a lot of UPC codes is use dynamic memory allocation, namely malloc and free, for allocating things like linked lists and trees and graphs and so on. There is a version of malloc called UPC alloc, which is going to allocate something in the shared space. If you just use the regular malloc, the C malloc, because it's C code, it's just executing things in the private space. Just one thread can call this, and it allocates something like this, this array of n doubles. So you can see the picture that it lives in that chunk of the address space that's got affinity to thread 1 right there. That's pointer P2. Now, in that code I showed you, this red line of code here, which is the shared double of the UPC alloc, where it's allocating. That's what's allocating this array right here, or declaring P2, which puts it down here, and then allocating the array, which puts the array of doubles right here. If that code can be executed by only one thread, and that's fine. And it's now up to you as a programmer to worry about whether you're going to take that pointer, hand it out to some other processors. When is that data structure going to get freed? Is it still around when they're going to use it? But it's kind of explicitly under your control, just as it is in a C program, right? If you allocate something in a C program and you free it and then you try to access it later, bad things happen. You have to keep track of when things need to be alive and when they're done, and you can free them. So this can occur inside of a function, which is why it may look exactly like the picture I have here, but it also can occur in part of the code where all the threads execute it. It's not collective, but they can happen to execute the same code, and they can all get chunks that'll look like that. So if it's not executed in a branch, the picture of what the data structures look like will look like this. And there's a corresponding free function then to deallocate space. There is a collective way of doing this called UPC all alloc, which is down here, and there's also a global alloc, which allows you to allocate a array that's spread out over the system. I highly recommend you use, if you're going to do that, you use the collective version of it. It's much easier for all of us that write compilers to implement. Because all the threads just allocate their own chunk, and then you just have to share the pointers so that every processor will get the same pointer back, which is the pointer to the beginning of the array. This global alloc will allocate a big distributed array. It's fairly tricky to implement on some of these systems because you've got one thread allocating memory on other threads, and it can be done, but it's just a little bit trickier, and so there's comments about it in various implementations, and I don't recommend it because it tends to be slow. If you want some more sophisticated data structures, what do we actually do in UPC programs? This is a picture of what we use in the NAS multigrid implementation, which has got a 3D array in it in which you're doing nearest neighbor computation. So what do you want to do? You've got a big 3D array. You want to chop it up into cubes, which are three-dimensional structures, and you want to give each processor at least one of those cubes, maybe more of those cubes, and that's in fact what this data structure does. We call this, and this is sort of informally in Berkeley, we call this a directory-based implementation of these data structures. What you have, and here's just a simple picture where each thread has a pointer to one chunk of memory. This is the directory up here, and that pointer is replicated. That is, the pointers each point to a different chunk of memory. So from this directory, you can get to any other thread's piece of memory. You notice that the address space partitions are curved here. They go around a corner because I couldn't squeeze it onto a slide otherwise. But if you've got a three-dimensional structure, then the directory itself can be three-dimensional. And each processor can have a copy of that directory. So they each have a copy, and what each one of them has is exactly the same set of pointers. That is a pointer that points to the red, blue, green, and whatever yellow, brownish chunk here. And so from that data structure, they can get any piece of it. You can walk through this directory structure and ask whether or not the particular pointer points to something local, then do all the computation on it. You can find your neighbors in it very easily and things like that. So these are much more general sort of data structures than the UPC arrays. It allows you to have ghost regions and things that you may need. Because you have shared variables, as in OpenMP and in pthreads, in I guess ISO-C now, they have recognized the need for understanding the memory consistency model. The memory consistency model tells you what order the threads are going to be able to see the accesses that another thread is performing. If you write a program that has races in it, that may just be a buggy program, but it may be a program that you intentionally have races in because you're trying to, because you have variables that you're using as sort of your own user-defined blocks. So here's a little program to consider. You've got some data that you're writing in one thread, and then you write a flag when you're done writing the data. Another thread is spinning on the flag, waiting to see whether the flag has been written, and when the flag has been written, it will act, once this thing becomes true, it'll fall into this and actually read the data. Okay, so imagine data is some big complicated data structure that's being written. Flag is just a single variable that you're reading and writing to determine whether or not you've gotten here. This is not a lock. There's nothing special about the flag variable. And UPC has two kinds of accesses. It has what are called strict accesses that appear in order. So if data and flag are both strict variables, then their accesses will be strictly observed, and that means this program will work correctly. If they're relaxed, then it says that although this program thread will see its own reads and writes happening in order, other threads may see things happening out of order relative to that, because the compiler may reorder them, or the network may reorder them. Maybe the easiest way to think about this is imagine that flag is sitting locally with affinity to you. They're both in the shared address. They're both in the shared address space, but you have affinity to flag, but you do not have affinity to data. It's living someplace else. So you write data. It takes a long time for that write to get there, and then you write flag, and that's very fast. And if you're using a relaxed ordering, the flag can be written before the data is written. So you need to be careful then about using these strict operations. These are similar to memory fences that you have in, and in fact there is a version of a memory fence in UPC as well. So first of all, I'm going to show you one cartoon of an implementation of UPC. This is the Berkeley UPC Compiler. It is it's open source. It's you can download it. We give out CDs for it every year at Supercomputing, so either come to the PGAS booth where we'll give out UPC CDs, or you can just download it from the web. But if there's so many people at Supercomputing, we figured we wanted to make it easy for everyone to write UPC programs on the plane on the way home, so that's why we hand out CDs as well. So it's got 4 layers in the runtime system, and then it's got what we call the compiler. Now we sometimes call this the translator, because what the UPC compiler does is it takes in UPC code and it spits out C code. So it's what's called a source-to-source translator. It doesn't generate assembly code or machine code or anything like that. And so this is because we wanted the Berkeley compiler to be very portable. One of our goals when we started this project, which was about 15 years ago, was that we wanted to, 10 years ago, we wanted to make UPC universal. We wanted it to run everywhere. And at that point, the language tended to be a little bit more restricted, like Cray had an implementation. They still have their own commercial implementation, but we wanted a compiler that was going to work on machines like the Blue Gene, which at the time IBM didn't have an implementation for, and also we wanted to work on generic Linux clusters, InfiniBand clusters, even Ethernet clusters. You can now run UPC on top of an Ethernet network. It's slow. Dereferencing a pointer on an Ethernet network is not something you want to do very often, but it can be implemented if you want to test code that way. And it also runs on top of shared memory machines, on top of multi-core and multi-socket SMPs and things like that. So that's why we generate C code out of the translator. We don't tend to do a lot of work in that. We've had research and compiler optimizations for a while, and I've had a couple of PhD students that have done work in that area, although at the moment the UPC compiler is sort of fixed. There is a GCC-based implementation that I mentioned before by a company called Intrepid. That's called GCC UPC, or GUPC, and it is being merged into the trunk of the GNU compiler, so that will help with the kind of long-term sustainability of that implementation to be part of the standard GNU release. But theirs is actually generating assembly code out of the back end in whatever, for whatever GNU, the GCC compiler supports. So the Berkeley compiler then takes this compiler-generated C code and then calls to the UPC runtime system. And the UPC runtime system is compiler independent. That UPC runtime system is also used by Intrepid, this blue part here. Underneath that is really the bulk of what's in the runtime system is this communication layer called GasNet. This is a one-sided communication layer, and that's actually used in a number of other languages. So it's used inside of at least some of the implementations of Chapel that you'll hear about later. It's used in the Titanium implementation. It's been used in a graph library, distributed graph library, and things like that. So there are a number of different places that GasNet has been used. And you can, by the way, use GasNet as a standalone library. It was never intended to be used as a application level library, but if you're C programmers, maybe you'll find it, you can get everything you want at the GasNet level. And then of course underneath that is the network hardware. That just shows you what I said, that the Berkeley UPC compiler and the GCC UPC compiler both use that, and there's some of the other things that use the lower level layers. Also when we started this project, the word on the street was these partitioned global address space languages are really convenient, really easy to use, but they're not very high performant. And we sort of took on the task of trying to disprove that and say, no, you can get very good performance out of the PGAS languages. In fact, in some cases, you can get better performance out of MPI programs. Now, when you get into high performance UPC programming, you do start worrying about the details of where things are laid out and exactly when communication is happening, but you are doing it based on one-sided communication. So you should think of those highly optimized UPC programs as programs that are using explicit, in fact I didn't mention that slide must have fallen out of here. There are library calls to do non-blocking puts and gets in UPC, so you can do bulk puts and gets inside of the language as well, just as you can do sort of mem copies in C. What is the one-sided versus two-sided story? So what's the difference between a one-sided and two-sided message? Some people have said, well, how can you possibly have a one-sided message when the whole point of a message is to communicate? There are, of course, two processors involved in this, or at least two nodes in the network. We'll take a two-sided message first, so the second thing here. So in a two-sided message in MPI, what you have is some data payload, the stuff that you're going to send, and you have a message ID. So the message ID is something that is made up by the MPI implementation. And so that message comes across the network and it goes into the network interface, and it has to be, they have to figure out that message ID goes with a receive operation that is coming from the host CPU on the other side. In the receive operation, it has to match the send and receive together. Okay? Now, in a good, highly optimized MPI application, the programmer will have pre-posted their receives. So the receives will have already been posted in a table, so that matching should be very fast. There have been, at least historically, a few machines in which you can actually download, offload, put the receive table down into the network interface so it can be stored here and the data can be written directly to memory, but that's pretty unusual. So fundamentally, though, the information about where that message goes comes from the receive side. It doesn't come from the send side, because the send just says, send it to this processor, this other process in the MPI program, and ask it where the data goes. So the fundamental difference in a one-sided message is you've got the same data payload, but you've got an address rather than a message ID. That address says exactly where this thing goes in memory. And a smart network interface, and by that I mean an InfiniBand network interface, Cray, IBM, almost all of these will have RDMA support, and they're going to be able to take that data and write it directly into its final resting place in memory. So from a programming standpoint, what that means is that you need to think up front about where your data is going to live, and the other processors have to have the information about where to put things in yours. So it does require some upfront work to build your distributed data structures, maybe having pointers inside of them so they point to the pieces of the data structure. But once you have it set up, then you don't have to involve the host CPU on the other side to ask it where to put the data. You just directly write it into the remote memory. And that's physically what happens. Even in the lower levels of an MPI implementation, they will use an RDMA level because it's the most efficient mechanism. So you can think of this as exposing the most efficient thing that the hardware does inside of the programming language. This is what the bandwidth differences look like for Berkeley UPC, Cray UPC, and Cray MPI. So the lower green line, this is bandwidth, so up is good, right? You want these to be fast, and this is message size across the x-axis. So eventually you get up to a message size where they should, UPC and MPI should all hit the same peak bandwidth of the network. Something a little weird is happening inside of the MPI implementation here, and I'm not sure what that is, but this is sort of typical that MPI will catch up eventually with what happens in UPC. Something weird is also happening in the Berkeley UPC implementation right here. I think we do know what that is. It has to do with the switch point probably being wrong, or at least tailored differently in the two implementations. But you can see that Berkeley and Cray both basically are, other than this one data point where Berkeley is way off, they're the same, and they're consistently faster than the MPI implementation. Now this is what we call a flood test. This is where the processor is sending messages out into the network as fast as it can. So even when you say an 8-byte message, it's not just sending an 8-byte message, it's sending 8 bytes, 8 bytes, 8 bytes as fast as it can. And so the real issue is that the overhead of sending a message is lower in UPC because they're using that lower level RDMA mechanism directly, and therefore you can get higher bandwidth. You can saturate the network more quickly, and you can get better bandwidth for applications that need to do this. And this shows you the relative speed of the two, and there again you get, at least on this, you see that UPC over MPI does have a significant advantage here for small to medium-sized messages. So if you're sending really huge messages from a performance standpoint, it doesn't matter. You know, it may be that you can get the same kind of performance out of the MPI one-sided. It may be depending on your application, you will or will not see these effects. But the point is that you shouldn't think of PGAS as something that's really slow. You should think of it as something in which you've got your hands on the lower level network layer, and you can program it to be as fast or even faster if you program it carefully. This is some old data from an InfiniBand network, just to show you that it's not just a Cray system. This is even on a Ohio State's implementation of MVAT pitch. That's a fairly old MVAT pitch implementation because this is an old graph, but you do see a significant difference here again in the bandwidth between the GasNet, the one-sided GasNet implementation, and the MPI implementation. This is point-to-point. This is just a single network. That's a very important point, and in fact, something I don't have the data on, but we did have we have a paper that we recently wrote, hasn't been published, on congestion issues. So one of the disadvantages, I mean, just to tell you the truth, one of the disadvantages of being able to push messages out in the network as fast as possible with very little overhead is you can saturate that network, and bad things happen in the internals of the network. So you could say, oh, MPI always meant to have overhead in there, and because of this handshake that happens in many of the MPI implementations that keeps you from flooding the network. So there's a kind of a natural, so it's sort of like everything runs a little bit slower, but you can't push it over the edge where everything backs off exponentially, and then all kinds of bad things can happen. So it is a real issue, and an issue also that we're doing a lot of work on right now is worrying about the number of threads you have per node that are all sending out into the network, and that's another big issue, which is saturating that part of the network, saturating the internals of the network. All of these things can happen. So latency, this is on Hopper, the XE6 system that I mentioned at NERSC. So this shows a latency difference between MPI and UPC. I think the two-page sizes, one of them actually didn't show up here. It's a line in between here for the, for the large page sizes, so they get a little bit closer. And here is, here's the bandwidth difference. There's UPC and MPI. And once again, sorry, when I copied this slide, I guess it didn't copy the colors over very well. But the UPC implementation is still better in terms of bandwidth on this system until this point where something is going wrong in the UPC implementation. So we see these kind of results fairly consistently, but this is raw micro benchmark data with the wind at your back, nothing else happening in the network, all that kind of good stuff. And so exactly what happens in a real application can be different, and you have to worry about things like congestion in practice. So those are latency numbers and bandwidth numbers. We mostly talk about the bandwidth. A 4 kilobyte message is not a huge message. For very large messages, the two implementations should get the same bandwidth, and if they don't, that means there's something in the implementation that we need to fix. But typically, you do get the same bandwidth for very large message sizes. 4 kilobytes is not such a large message, and here's where you're at that midpoint in the graph where you're still seeing a gap, even though you're not at 8 bytes. Things are running pretty slowly anyway. So if you're doing all your communication with 8 bytes, you shouldn't do that unless you absolutely have to for algorithmic reasons. But 4 kilobyte messages is a place where you really have a natural advantage in terms of performance. And one of the places that comes up is in something like a 3D FFT. So a 3D FFT, how many of you know what a 3D FFT looks like? Okay, everybody basically does, or a lot of people do. But I'll just say, the important thing for this discussion is we're going to compute 2D FFTs on each of these planes, and then we're going to flip the layout. So the planes will be owned by a single processor, and then we're going to flip the layout so that, for example, one processor will own all the blue pieces of each plane, and then we'll do the FFTs in the third dimension after having done the first two dimensions this way. So if this is for what's called a one-dimensional partition, so I'm thinking that each processor owns a plane, but this also works, and you're going to need these same kind of ideas if each processor just owns a chunk of a plane. So you can think of sort of three different approaches for this model. One is called the chunk model, where I'm going to wait for all of my FFTs to finish locally. I'm going to pack all the little blue pieces together. Note that they may or may not be contiguous in memory, because if I own, let's say, two planes, the two blue pieces that I own are not stored in memory because they're stored next to the green things. So I have to pack them together to make them contiguous and then send them as a single message. For most, the kind of recommended MPI programming style is pack to the maximum message size because you get better bandwidth. You saw those bandwidth curves, right? They're better bandwidth for bigger messages. So you pack the data and then you send a bigger message, and that's the best thing to do on most MPI implementations. Now, at the other extreme is what we call the pencil implementation at the bottom there, and that says I compute, let's say I've already done the column FFTs before, and now I'm doing the row FFTs. So I do one blue row, and I immediately send that blue row to the processor that's going to own it in the other orientation. So I don't have to pack anything because that row is still contiguous. It's going to get sent to the other, each row is going to go to a single processor, and so that can be, we can start sending much earlier. So by sending pencils, we can start the communication earlier, actually end it perhaps later, and overlap communication over a longer period of time. So the name of the game here is what they used to call in the connection machine, a really old machine, all the wires all the time. The expensive thing you're doing on these systems is communication. You want to maximize utilization of the wires. You want to always keep those wires busy doing useful work, right? Not sending junk into the network. Slab is somewhere in between, where I say I'll compute all of the blue rows on one plane and send that one plane. Depending on the machine characteristics, each one of these will, some of these will pay off more than others. On some systems, the best thing in UPC is pencils. The best thing in MPI is chunks. That's because of the difference in overhead of sending messages on those. So you can't afford to do pencils if your overhead is high, because each one of those pencils has an overhead associated with it. Here's from the Blue Gene P system here, the older Blue Gene system. This is looking at the UPC implementation. There's both a slab version and one that uses collective communication, one that packs slabs together, and then the comparison to the MPI implementation, which is the black line that's roughly at the bottom consistently. So UPC consistently outperforms the MPI in this case. All of these are using a highly optimized local FFT library, so we're not comparing FFT implementations at all. They're using the same FFTW implementation. Actually, I think it was probably IBM's FFT library. The UPC version avoids that send and receive synchronization because you've got to match up those sends and receives, and so it has lower overhead, better overlap. And the thing that was actually surprising to me when we first discovered this and thought about it is better bisection bandwidth utilization, because, as I said, you spread your communication over a longer period of time. If you're limited by bisection bandwidth, that means how much you can shove through the entire network from all the processors at once. You're better off if you start that as early as possible and spread it out over a longer period of time, because you're sending the same volume of data, but you're allowed to send it over a larger period of time, and you're overlapping it with useful work. These are pretty good numbers in terms of the peak performance coming close to the HPC challenge record. We haven't ever run a big enough problem to actually get our own number for that, because you need a big access to a big chunk of the machine. These are numbers on the Cray XT4, that's an older system at NERSC. So the next thing I want to talk about is kind of a different model. So FFTs are still an all-to-all model. It's a perfectly natural application to write in MPI, because you mostly compute and then you communicate, and even if you're going to do a better overlap of communication and computation, it's still pretty easy to orchestrate that because all the threads know. It's a very fixed pattern. You know what is happening when. LU factorization, of course, this is what's in the HPL, the LINPACK benchmark. much maligned as a terrible benchmark because it is dominated by BLAS 3 matrix multiply performance. It will be surprising to you if you've never worked with this application how badly it runs if you don't tune it very well. Okay, so yes, it's dominated by matrix multiplies, but you can screw it up in many possible ways, and it will perform really badly because there's a lot of dependencies in an LU factorization. What are you doing? Well, you're factoring a column, you're kind of broadcasting that out to the top row, then you broadcast the blocks down, you're doing trailing matrix updates, these rank K updates on those little orange and yellow blocks that are down there. Those are the big matrix multiplies. So this thing goes fast as long as you can always keep the processors busy doing those orange and red things there, not tied up waiting for the blue and green things. So it's really important that your synchronization is not getting in the way. And the easiest way to write this, and in fact the way it's written in the Scala-Pack code, the original Scala-Pack code is factor your column, do a barrier synchronization. So not all the processors are busy there. Do a barrier synchronization, wait for that to complete, or at least a logical barrier. Then do the triangular solve at the top, do another barrier, and then do the broadcast down, and then do all of the, then treat that thing as a big matrix multiply. It's a great software engineering idea because I have this big distributed matrix multiply, which is the thing I'm doing on the orange and yellow blocks. And so I can just think of matrix multiply and make that thing go really fast. But I just wasted a bunch of time waiting for synchronization where the processors were not busy when some of those blocks were actually ready to be computed on. So in the HPL implementation, unlike the Scala-Pack implementation, when people really are trying to get the best performance, what they do is they have what's called look-ahead, or they have multiple panels that are in effect at the same time, and there's a tuning parameter that says how wide that is and how many panels you're going to have going simultaneously. And you allocate a bunch of extra memory in order to allow for the incoming green and blue blocks to store them so you can do the trailing matrix updates. So the same thing is done in the UPC implementation, except that it's all event driven. So in the UPC implementation, it's actually done with a Berkeley UPC extension of UPC, which are called semaphores, where you can send the data and there's a little lock that happens on the remote side. The whole thing then is written in this more event-driven style, and the idea is just to keep the processors busy all the time. Now, an interesting thing happened in the first implementation of this. It was done by Perry Husbands. Somehow his name fell off the slide, but anyway, he did all the hard work of figuring this out and implementing it. He had actually done the tuned implementation of the LinPack benchmark on the previous NERSC machine. At the time, it was an IBM SP3, I think. That was the machine that several years ago. So he knew very well what happened in HPL. But the first implementation of UPC he did actually deadlocked the memory allocator. What did this mean? It means that you need to allocate memory for these temporary blocks, the blue and green blocks that are coming in, so you can do the matrix multiplies on those things and then add them to the yellow and the orange blocks. And the problem is you want to make sure that the critical path in this thing executes in order to make forward progress, but you're keeping the processors busy by doing matrix multiplies whenever they have nothing better to do. So you allocate memory to do those matrix multiplies, and at some point you're waiting for some block to be computed, but the processor has tied up all their memory doing matrix multiplies, and they can't execute it until you finish something that they're waiting for. So it's a classical sort of deadlock problem, but it comes up in the memory allocator. So the solution in this case was an application-specific scheduling policy that controlled memory allocation so that you didn't get ahead of yourself in some sense and allocate more memory than you could afford to allocate. So you always had enough memory left to execute the critical path behind you. There's the implementation. This was compared to HPCC numbers, the HP Computing Challenge, because we didn't try to run it on the whole machine. Whole machine runs, by the way, take on the order of a day or so, and machine has to stay up the whole time, so we didn't feel like it was a good use of the machine to do that. Plus, we didn't actually have access to it, although I guess I was nurse director at some point. I could have said, we're going to do that, but it didn't seem like something I should do as nurse director. So, but you can see the numbers are comparable to HPL, which is also highly optimized in terms of overlap. Other things have been written in UPC. There are a number of papers, some of which I haven't even had a chance to read yet, on other applications, scientific codes written in UPC. This is a QCD benchmark called MILK, written by somebody at Berkeley. Hongjiang Shan did this work, and this is the UPC version compared to, as you can see, an MPI implementation that was pre-existing. So he did, you can see that it benefits. Now these things can be highly suspect because in my opinion, the most important thing is the Well, the second most important thing is the machine you're running on, and the most important thing is the programmer who wrote the code. So the language is only one small factor in here, but you can get pretty good performance out of UPC. UPC is not the only PGAS language. You'll hear a lot more about Chapel. I'll just mention some of the other things that are going on and have gone on in the past. I worked for a number of years on a project called Titanium. It was a Berkeley research project. It was a beautiful language, much more beautiful than UPC, based on Java, and had a lot of interesting compiler analyses. We proved deadlock freedom. We made sure you couldn't have aligned barrier synchronization in that language because the compiler wouldn't allow it. And there were a lot of other things that we could do in the compiler because the type system is strong enough in Titanium. You can do a lot of analyses. You can automatically convert global pointers to local ones and make them faster and things like that. Co-array Fortran, which is, there's a co-array Fortran 2.0 project from Rice, but a previous version of co-array Fortran is in the standard Fortran, in the Fortran standard at this point. It is a subset of the features, so that's a PGAS language done in Fortran. I don't think you have a CAF lecture here, but anyway, X10 from IBM is another one of these languages, and then Phalanx, which was a project that I worked on as part of the DARPA Echelon project, which was led by NVIDIA, also has C++ PGAS-like features, and I'll say a little bit more about that. What we are looking at now, UPC has a user base. It has applications that are used in production, and so that effort is ongoing, but we're also looking at more modern languages than C, so we're looking at PyGAS. And lots of interesting things come up because PyGAS has a managed, Python has a managed runtime system. It also has the GIL, the global interpreter lock. So anyway, running lots of copies of the, so running one interpreter per node and having 128 threads all grabbing that global interpreter lock is not a good execution model. So there's lots of interesting problems to solve inside of that. Here's just some other performance results. This is actually co-array Fortran, and this is there was some people that did work at Berkeley on a landscape analysis, which is looking at estimating rainfall and how it flows. There's a gyrokinetics code used in fusion simulation, so this is GTS. This is just the shifter part of the code. That was an SC paper from a couple of years ago. This is running time, so down is good, and the co-array Fortran are the lower lines there. Kind of to summarize UPC, and I'll say a little bit more about these other languages, it was designed to be consistent with C. It takes the good and the bad parts of C, so the ability to use pointers and arrays interchangeably is one of the things that I both love and hate about C, and UPC has that as well. It makes compiler analysis really difficult because the type system is fairly weak, and so it's hard to know exactly what's happening at any given point in a static piece of code. It's designed for high performance. The memory consistency model is explicit. It's a relatively small implementation, so unlike high performance Fortran, if you're familiar with that whole history, it had a very sophisticated compiler that was required to make it successful. Although we've put a lot of work over the years in the Berkeley compiler, and the Intrepid group has as well in the GCC compiler, most of that work actually is in the runtime system. That is in making GasNet work well on each new interconnect that has its each new and interesting features, and that can be used in multiple languages. I want to step back because I think earlier, near the beginning, there was a question about understanding where the data lives versus this idea of threads. And just to be clear, because you're going to hear about Chapel, I think it's important in your mind, and people use these words sometimes interchangeably, that there's a question of what your control model is in your parallel language or your parallel library, and there's a question of what your model is for data and sharing. You've got to have some way of sharing or communicating, because you can't do anything interesting in parallel application if you can't communicate. And so, two of the models you've seen are send, receive, and load, store, put, get, whatever you want to call the load, store things that are one-sided. Those are fundamentally one-sided operations that go from one processor into memory. Send and receive are fundamentally two processes involved doing the communication. And really, that's what I think makes PGAS PGAS. It's about this question of what the sharing looks like. It's load, store, but it has a logical partitioning between the address space that has a performance implication to it, so you can optimize for performance. The control model is the question of whether you have a fixed number of threads that run from the beginning of the program to the end of the program, SPIMD, which is on the right here, and that's what UPC has. Does it have dynamic thread creation, which is, by the way, much closer to what was implemented in the LU factorization implementation, where threads were basically being created on top of the UPC fixed threads to dynamically execute tasks such as factor this block or multiply these two blocks together and add them to a third block. So that's a more dynamic tasking model. And then there's data parallelism, which is really more of a serial semantics where you're executing a series of, for example, array operations and other things. But logically in the programmer's mind, it looks like serial code other than the fact that there's these array operations. Much more elegant, much easier to think about these. But you can have these different kinds of communication models underneath these different control models. Maybe data parallel doesn't fit so well with send and receive because you've kind of got a serial semantics there, but you have this idea of a global address space. So I really want you to kind of take away the idea that PGAS is this partitioning for locality. What we're missing right now from UPC, and I alluded to in the LU factorization example, is a signaling store. That is the ability to write remotely and have it trigger something on the remote side. And it is something that's in the Berkeley implementation, but not yet standard across the languages. That's very important for producer to consumer kind of parallelism. So at this point, send and receive tends to be a better model for producer consumer parallelism. But it's not necessary to have the receiver receive at that point in time, right? What's necessary is that you have a place to put that data and then you know whether or not the data has been received. And SPMD is the default in UPC, but you get kind of a data parallel style in UPC by having collective communication, and you get dynamic tasking through libraries. I didn't mention it, but we do have a dynamic task queue library that you can use from UPC that's built on top of UPC, so if you want to dynamically load balance things, it's something you can definitely do. Just to say a little bit about some of these other languages, so in Titanium, which has much more sophisticated multidimensional arrays, and this will maybe look a little bit more like Chapel or X10, you can manipulate these multidimensional arrays more directly, and it gives you a lot of the, I think, the programmability and convenience advantages that you get from these languages. So what you need in addition to the global address space is the ability to really talk about the data structures that you want to manipulate. So in this case, Titanium was designed with Phil Colella, who does adaptive mesh refinement computations, computational fluid dynamics. He was involved in the Titanium design effort, and he knew that he wanted adaptive block structured meshes. So there's a little picture of what they look like. You've got a hierarchy of meshes. Each one of them is rectangular in this case. You want to do things like project up and down between different meshes. And so you often want to take two meshes that are next to each other logically in the physical domain and then calculate some overlap. You know, for example, average between the points that are on the neighboring values. So if you, in that kind of a world, when you want to do something like fill in the ghost regions of all of these little blocks with multidimensional arrays, it can be done very conveniently using both the combination of the global address space and the higher level array library. So here's the copy operation. It just says copy grid, do a copy onto grid B from grid A, which is shrunk by 1. So grid A is this blue thing. We say, well, we want this interior region. So I don't make a copy of grid A. I just logically think of the interior region, and I copy it onto grid B. That copy operation automatically from the compiler and runtime implementation computes the intersection, which is this little green sliver. So there's a whole bunch of code that's hidden down in there, which is not very interesting code, but unfortunately pretty easy code to get wrong. And you get a mistake in some of that code, you have a little off by 1 error, and suddenly your solver doesn't converge anymore, and it can be really hard to track down. So this is all about software engineering and code reuse, trying to minimize the number of people that write that kind of code so that you get it right once, it gets debugged, and hopefully use it many times. And in a language like Titanium, then this shows the difference in there's performance. A comparison between the Chambo implementation, which was done in C++ and Fortran, is still a very active project, and the Titanium implementation, so the speedups are comparable. I think Chambo is a little bit faster. There's the differences in the number of lines of code, and divided up by the different parts of the library. Now you could say, well, the array library in Chambo is also reused many times. It's reused by Chambo users, certainly, but whereas there's the array implementation Titanium is down in the language implementation, and therefore is reused by anybody who writes Titanium code. So that's how we'll get better productivity out of these kinds of languages. So this is a particle and cell method, and this was an algorithm and implementation from Charlie Peskin's group at the Courant Institute at NYU. They're doing the computational fluid dynamics of the heart, and we re-implemented that code in Titanium So we were not doing algorithm development here. We were just doing, we designed a new language and then completely rewrote it from scratch, and that's the heart actually beating inside there. And all kinds of interesting things happened, and we learned lots about the language from doing a real application like that. So now I mentioned before PGAS. It's combining two popular ideas, Python. It's number 6 on the LangPop website for whatever that's worth. And you know, one of the things after having worked on languages for many years, what I've realized is, in some sense, it doesn't matter what the language looks like. Why do people use languages like Tickle? Why did they use Tickle when, you know, by any objective language measure, it was not the most beautiful language? It's because it had libraries that went with it. So why do people use Python? Well, you could say it's got some great features in it, which is true. It's also got some not so nice features in it, which is also true. But it has a lot of libraries, and it has a lot of libraries in the scientific computing community. So there's a piece of the scientific computing community that uses things like NumPy and SciPy. It gives you interfaces on top of things like MATLAB. It also has its own built-in multidimensional arrays. It's got things for plotting and for things for communication. And there, of course, is a version of MPI as well. And then PGAS, which gives you the convenience of data and object sharing. So we have a little implementation of PGAS running, and we're now going to step back actually over the fall semester and look at kind of what this means from a language design standpoint. What do we want this language to really be? It's built right now on top of something called duck typing in Python, which allows you to basically have these proxy objects when they're distributed. We've got distributed pointers or global pointers in them. For those of you who are interested in UPC, what we've also found, for many years, Bill Carlson and I were asked, since he was involved in a lot in pushing UPC from the very beginning, and continues to be, that why don't you do a UPC++? And the answer was because I saw people doing C++ based languages, and they never could get beyond we're implementing the UPC compiler, and as soon as we get it working and it can compile all our programs, then we'll start doing interesting research in compiler optimizations and so on. It's really hard to implement a UPC compiler, a C++ compiler. There are standard front ends, for example, EDG and so on, that people use, and we worked with that for a little while. But what we have done more recently, and this actually came out of the Echelon project with NVIDIA, was and it's because CUDA is based on C++, to put CUDA into UPC, what we ended up doing is building a UPC++-like language, which is based on operator overloading and things in the UPC. So there's no compiler here. It's just using the usual tricks in C++, but you can get things that look like global arrays. You can dereference them and have a remote put operation by using the overloading, and you can have a remote get operation as well. So, and there's some performance numbers that show this thing actually does scale pretty well, and running it with a few different simple applications. This is something that I don't think of as really a research activity in terms of language design, but it is something that's very practical for those of you who are interested in trying out the PGAS ideas, but maybe want the kind of support that you get in a language like C++ for abstract data types. UPC++ and this library approach may be the right thing to do. So you can really get the one-sided semantics, and you can also, I should also say that we often mix together UPC and MPI. In fact, we use MPI as collectives because, as I said, we're not sure that we like some of the features of the UPC collectives at this point, and so we often mix together those implementations, and that's certainly possible. What we're looking at kind of going forward is a more hierarchical SPIMD model. This is something that already exists in MPI, and there are a notion of communicators, but it's something that really hasn't been in UPC before. So the ability to take a big domain, the machine, so you've got this fixed number of threads, and you want to divide it up into pieces. So for example, we want to partition the threads, and that's what this little bit of code looks like. This was actually titanium extension, into the code that's doing the fluid, the code that's doing the muscles, and the code that's doing the electrical part of, say, a heart simulation. So this hierarchy is useful in some applications that really have multiphysics in them, and you want to couple together these different multiphysics models. It is also useful for hierarchical machines, because what we find is even if you want to use UPC everywhere, you can use UPC very conveniently within shared memory, and it performs very well, and you can use UPC in distributed memory. There are cases where you want to use different algorithms inside a node than the algorithms that you use between nodes. You may want to copy state between nodes that you want to just share directly within nodes. And so for that reason, you may want to use different implementations. So we're using this idea of a hierarchy, and we'll be looking at that also in PGAS. And let me just say that I think this one-sided communication idea, is also not just something that you want to use in the network, although it certainly, as I showed you, is something that I think is useful to use in the network. So it's the RDMA mechanisms that come up in networks like InfiniBand and the HPC networks mean that you can usually get very efficient implementations of one-sided put and get operations. But these DMA one-sided operations also is a very natural fit for things like moving data to and from accelerators, so GPU to CPU, moving data to and from I/O systems, whether it's an NVRAM sort of implementation, flash memory, or you're going out to disk. What do? You do an RDMA or a DMA operation to move the data. So a one-sided model matches both a single level hierarchy and also a parallel processing model, because you have a single thread that is writing to and from this device. So I think that this is going to come up more, and so we're looking at kind of a vertical idea of PGAS, where as opposed to the horizontal partitioning that I've shown you in all the other pictures, in this case what you have is, say, private on-chip memory and then memory that's off-chip at different levels, and you've got a vertical partition that you're using. You can end up with a lot of different pointer types. That can be a kind of a hindrance from a language design perspective. A lot of what I've talked about in terms of the performance of UPC is all about communication. And what you, I'm sure, have heard from earlier talks this week is communication on these machines is the most expensive thing you do. It's expensive in time. There's some annual improvement rates for network bandwidth, network latency, so they improve by 15-25% per year, as opposed to flops, which still improve by something closer to over 50% per year, not in the rate at which each individual flop is happening because of the problems that we've had with clock speed scaling, but you still put more and more cores in the chip, so you're still getting this gap between the improvements in latency and bandwidth, which is already high, and the improvement that you're getting in floating point performance, aggregate floating point performance on a chip. It's also expensive in terms of energy. This shows the energy that's used to perform an arithmetic operation on one of these systems, so this is picojoules, and the amount of energy that's used to move data from these different levels of the memory hierarchy. As long as you're on chip, you're fine. It's probably about the same amount of energy or less energy than you use to do an arithmetic operation, but it goes up by 1 or 2 orders of magnitude as soon as you go off chip. So that says that the big cliff that you fall off of in these systems is not even between nodes, it's between the processor chip and the DRAM. And or whatever that memory is going to be. So as soon as you go off chip, you're starting to consume a lot more energy in the system. So that means we really need to optimize communication. There's a couple of different ways of looking at communication. Of course, there's the bandwidth, which is the total volume of the thing you're sending, and there's the latency, which is the number of separate messages that you're sending. We can do a lot to hide latency, and that's what UPC is all about, right? It's all about trying to give you low overhead communication so that you can afford to start communication early, you can overlap it with other computation, and you can often hide the latency that's involved in sending a single message. UPC doesn't do anything to help you reduce bandwidth. If you want to reduce bandwidth, you have to do something at the algorithmic level to figure out what it is you're going to, how it is that you can send less data and still compute the same answer. Now these things from a system administrator or a nurse director perspective are very hard to change. So users will say, we want more bandwidth, we want lower latency, we want faster processors, but these things are really hard to change. So latency fundamentally is going to be limited by the speed of light, which is physics. So we can't do anything about that. Now we can do something about software overhead, because most latency today is actually limited by software overhead. So you can try to reduce the software overhead, and that's what one-sided communication is about. Bandwidth, on the other hand, is merely money, not as hard to change maybe as physics is, but actually in practice it's equally impossible, because even if you put all of your budget, 90% of your budget in bandwidth, you would still have a system that could be imbalanced in terms of the bandwidth versus the compute speed when you look at where the trends are going. So it's just very hard to actually have enough bandwidth. And the incremental cost of doubling the amount of communication is so cheap, doubling the amount of computation is so cheap relative to even adding a little bit of communication that's why systems look the way they do. So what do we do about bandwidth? So this was something that we studied for many years, looking at sparse matrix algorithms, which are notoriously bandwidth limited, both on a single memory system and on a distributed memory system. And it was very frustrating because it felt like, well, you had to read the matrix. There's nothing you can do if you've got to read the matrix and you're limited by the amount of bandwidth that it requires to read the matrix. But there is a class of algorithms called communication avoiding algorithms. And the question is, can you prove for a particular algorithm what is the minimum amount of data that you can move in order to perform that computation? So we'll go back to matrix multiply just to give you an idea of what this argument looks like. This is the iteration space for matrix multiply. So the way to think about this is every plus and multiply operation that happens is one of these little cubes inside of this three-dimensional space. The projections, the faces, the red face is the A matrix, the blue face is the B matrix, and the green face is the C matrix. Obviously, they're on two sides, but you're projecting out a point in that middle of that space has an I, a J, and a K value. If those are the indices, I, J, and K. And so you're iterating over I and J for the A space, for I and K for the B space, and so on. For the A space. And so those give you these projections. And the question is, if I've got this computation, which I'm now thinking of as a bunch of points in space, what is the maximum amount of computation I can do for the minimum amount of surface area? So it's a geometric argument. It's a surface to volume sort of argument. And for matrix multiply, the question, you can pose the question of, given this computation I want to perform everything in the cube, I'm going to have to, when I pick up some piece, it could be some glob of stuff in the middle that I'm going to compute on, and I'm going to move the data that I need for that glob into fast memory, say into the on-chip caches, or onto the memory of each one of the parallel processors, because actually the same argument works both in serial and in parallel, but I'm going to move that into fast memory so that I can compute that glob of stuff. The question, what is the optimal shape for that blob? And it turns out, maybe not surprisingly, that the shape of that blob, the optimal shape is a cube. Okay, so that says that you want to actually chop up all three dimensions of matrix multiply, which is, by the way, not the way most people write matrix multiply. It is the way some people write matrix multiply. But a lot of times what you do when you write matrix multiply is you say, let me take the C matrix and use the owner computes rule. I'll give everybody every processor a block of the C matrix, and they're responsible for computing that block of the C matrix. And what that said is that you have not chopped up that dimension of the iteration space, and you actually you're not running an optimal algorithm. And it turns out that you can make matrix multiply go faster if you chop up all three dimensions. And what that means in practice is that processors are computing independently different parts of C, and you're going to do a reduction at the end and add them all together. Now, it turns out you can use the same idea in things like other kinds of loop nests, not just matrix multiply. This is a paper with my students that's looking at n-body. So this is actually very closely related to an algorithm that Mark Sneer did. We call this a 1.5D algorithm. The idea, maybe more intuitively, is what we call replicate and reduce. So we take the particles. So this is a really simple, dumb n-body algorithm that you're going to do an n-squared computation on. You take the particles and you replicate them over a certain subset of the processors. You also partition them then within each group. They independently compute some of the forces for some of the other particles within each one of those groups. And so they've replicated the state, and then they add it all together at the end. And so this idea also was used in a paper a few years ago that I worked on called on a particle and mesh method, where you replicate the mesh, and then you update those parts of the mesh and you add them together at the end. So it's a very general idea. Part of this is just observing that it really is the same idea coming up over and over again. But this shows that you can get a speed up of this 1.5D algorithmic idea over the usual domain decomposition. So don't just think about domain decomposition. There are places in which you can get better performance. You can't see the generalization because I've got all these nice little Mac icons on the bottom, but there's a pointer to a tech report that will be in the online slides that you can see if you want to look it up. The 1.5D paper was an IPDPS paper earlier this year. I've told you that UPC is really important, and you're going to hear much more on Tuesday about why communication avoidance is important. And so some of my students did was to work on the question of whether you want both communication avoidance and communication overlap. Or once you've avoided communication, in fact, we had a program manager that said, well, given that we're going to have communication avoiding algorithms, maybe we don't care about funding any research in networks anymore. We said, no, wait, that's taking the idea a little bit too far. And in fact, what this graph shows, there's a matrix multiply done with both the SUMA algorithm and Cannon's algorithm, a triangular solve and a Cholesky implementation. And although Cholesky we're still working on because we think there's some ways of getting a better performance out of both the avoiding version as well as the overlap version. But you can see most clearly in the two matrix multiply implementations that even after you've done avoiding, that is 2.5D, this idea of kind of replicating some parts of the C matrix and then adding them together at the end, so you get some significant speed up in gigaflops for that kind of an optimization. You get an additional speed up in terms of the gigaflop rate by also overlapping it on top of doing the avoidance. So these things are important. The bottom line is you really have to understand what's expensive in your machines and try to optimize it. And I'm just trying to leave you with the idea that while UPC gives you a really good abstract machine model that allows you to optimize for the performance, the fundamental performance limit of the network, and that's our goal in implementing GasNet, is always to expose to you the best performance that the network can possibly provide. You can't just limit your approach to looking at the runtime systems and things of that area. You also have to think about new algorithms. So with that, I will end and see if there are any other questions.